during your quiz, there was a single assignment about this issue, so about typecasting, and most of you failed this question. So once again, the integer promotion assumes that a single arithmetic operation has to be performed on data types of the same type. So even we have here in expression, we can have mixed types, so int or float together. When particular operation is performed, data types are converted. And the conversion way is defined by integer promotion. So if we have, for example, float and int, the integer variable is converted into float. If we have two ints, that's okay. But you should remember this. Okay, the second issue is related to precedence. So the importance of certain operations. So the precedence one means that this operator is the most important. So it has the highest priority, while this one, so comma, has the lowest priority. Looking at the arithmetical operations, you can see that multiplication, division, modulo, they have the same priority. Okay, so they are equally important. And sum and subtraction also has the same priority, but they are less important than multiplication. So like in standard math. When we have the operation consisted of several basic operations, the way how it is performed, so the order depends on precedence, but if we have operators of the same importance, the order is defined by associativity. So the order in which the operators will be executed. So if we have, for example, for division and multiplication, the associativity is left to right. So it means that the first operation will be this one, and then the result will be multiplied by C. Okay? In mathematical sense, it doesn't matter, yeah? Because, you know, we can perform this operation, you know, in almost in any order, but of course we should multiply A times C, not B times C. Okay, but in C++, it has some effects because if we know how integer promotion works and we focus only on this particular operation, you can see that A and B are integers. So the resulted value according to integer promotion will be integer 2. So what will be the value of A over B? Zero, of course. So when we multiply 0 by C, even C is, okay, C is integer 2, the result will be 0. But look here, For example, we have okay, so we don't have this example here, but if we even assume that C is float, so here we have float, it doesn't change the result because the first operation is 0. So even C is float and the result will be converted into float, the effect will be the same. Here we have different operations. So we have x here, x over b times c. So the first operation is this one. So if you take x float over b integer, the b has to be converted into float. So the result now is 1 over 2, but in floats. So it gives 0.5. So times c, it gives 1.5. So the result will be here. The result will be, what is the value of this? Yeah, so on the right hand, we have 1.5, but we have to cast it to d, so to integer again, so we get 1. So I hope it is clear for most of you, and you should be conscious that this effect exists. For example, we can imagine that we have an assignment. Let's try to so look, I'd like to write a program which calculates the body mass index. So this is the indicator which represents whether your weight is norm or not. Yeah? So to calculate BMI, we have to get two values from the user input. So enter weight and enter your height. So let's assume that the weight and height are integers. So we enter values in kilograms and centimeters. And now to calculate BMI, I need to take weight in kilograms and divide it by the height in centimeters, in meters. So I need to divide it by 100. And it should be squared. So the expression looks like this. So finally, I can display your BMI is BMI. Okay. So let's run this code. Wait. Okay. Let's assume that it is 80 and height one. Let's say 190. Okay. So you can see that your weight is 80. Okay. Do you know what is the norm for BMI? Okay, so look. Okay, so according your answers, yeah, the norm for BMI is about 18 to 22. The over 22, there is some grading stages of obesity. Yeah. So look, looking at 80, so it is impossible to have 80. Okay. So let's try to analyze what is the problem here. So I put a breakpoint here, and I try to okay. So 80, 190. Okay, so look. Let's try to calculate the proper value. So I have 80 divided by 1.9 squared. Okay. So it's about 22, not 80. So are you able to find the problems here? So look, because the result is 80, it seems that this value, so 80 is the weight. Yeah? So it seems that this value is equal to 1. Yeah? Yeah, okay, so if we change the type to floats, you can see that, okay, 80, 190. Okay, it's okay. So you can see that the problem is that it is related to incorrect conversion to integer. Why? If I have integer, 100 is also treated as integer. Yeah. So divided 100 by 190 by 100, it gives 1 as a result, because both of these elements are integers. So the result is integer 2. So the result is 1. So due to this event, the value of denominator is 1. So how we can cope with this problem? Of course, we can change the type into integer, but okay, it's not this is not our idea here. I'd like to show you how we can solve the problem when we have integer types in expression and we want to, protect this expression against bad integer promotion. So the simplest way here is to introduce, of course, static cast. It is my favorite one. But here we can use a simpler method. So look, I can introduce a literal constant, which is float. So now 100 is not 100 integer, but it is 100 of float type. So introducing this a literal constant forces to convert the height into float. Okay. So if I do it only in this point, you can see that. Okay, so let's run it. Okay, you can see that it doesn't work. So something was changed, but it doesn't work because I have two expressions. So the first one and the second one. So this expression has to be converted into float too. Otherwise, it is treated as the integer. Now it should work. Okay, so it works. Of course, we can remove braces here because this operation is still valid in this form. So look, in this case, this operation will be the first one. It will be converted to float. Then float will be multiplied by integer. So it will also, it is also converted to float. And then it is divided by integer, but because the left value is float, 100 will be converted to integer too. So, so in this form, the result should be also okay. But due to if we want to have a readability of this expression, it's better to to write it in form like this. But of course, there are another ways how we can solve this problem. So how we can cast types. So look, in C++, we usually use a static cast conversion. So we have to convert it according a static cast scheme. I need to write something like this, static cast. Here I have to write a type, so float. And as an argument, I have to pass the value, which should be converted to float. So this is the way how we explicitly convert values from one type into another type. So in this case, I don't need to introduce a literal, float literal, because height will be float. Okay. It is enough to convert, remember that due to integer promotion, it is enough to convert only a single element in particular expression. So the other element will be converted implicitly, so automatically. Yeah, static cast was introduced, as a standard about 5, maybe 10 years ago. But before this time and in C, usually the conversion was performed using casting on this way. So before the variable name, the type was written in braces. So this notation forced to convert B into float too. And the third possibility of conversion is casting by using literal constant. So it is enough to introduce the literal in expression. But remember, there's a difference. So if you have A, it's float, B and C, they are ints, and you want to calculate the result on floats. If you write, let's say, int A, B, okay, let's assume 1, 2, and float result is equal 1, 0 times A over B. It works, okay. Huh? But if you introduce a literal constant at the end of the expression, it doesn't work properly, because first, this operation is performed. So due to integer promotion, it is performed on ints. So the result will be integer. So it doesn't matter if or not you multiply it by float. Okay, so remember that if you want to use literal constant to force casting, you should use it as the first operation in your expression. Okay. So now I'd like to go forward. So I'd like to go deeper into types. So I'd like to tell you how types work, how values are represented depending on particular type, and what are the consequences. So hope you remember the binary system, so how values are represented in binary system. Now several terms. So first, I'd like you to know what is bit and byte, what the bit and byte are. Most of you know that bit or bytes exist, but in my according to my experience, some of you miss bits and bytes. So there is a misunderstanding what they are. The bit is the smallest unit of information, so it can be 0 or 1. And the byte, it's a group of bits. So you have 8 bits, which creates a byte. So what does it mean? when we have 8 bits? It means that using a single byte, we can represent values which contains the bits, all bits equal to 0 and all. So from this combination up to the combination where all bits are equal to 1. So it means that we have 256 different states. In IT, we usually express the amount of information in larger units, so in kilo, mega, or gigabytes. So look, kilo, it means 2 to power 10. So we have 1024 bytes here, not 1000 bytes like in you know, standard life. So therefore, looking at, for example, the capacity of your hard drives. Okay, sometimes it works different. So on hard drives, you have, for example, written that your hard drive has 500 gigabytes, but there is asterisk, and there is written that it means that it has 500 million bytes, not not 2 to power 30 bytes. So the amount of bytes declared on hard drives is usually smaller than this value. But in IT, the kilo, mega, giga means the decades of power with base 2. Okay. So looking at the capacity, there exists a term information capacity. So it expresses how many different states we can fit into a particular number of bytes. And of course, in binary system, which is typical for IT, the number of bytes is, or information capacity is expressed as the power of, so the number of bits is the exponent of which gives us the information capacity. So if we have 8, it's 2 to power 8, so 256. If we have, let's say, 1 terabyte, okay, we have 2 to power, let's say, 40. So it's a little bit larger, yeah? Okay. So now I'd like to tell you how types represents, so how type, particular type represents values. So look, we start from unsigned integer. So in case of unsigned integer, the 0 means all bits are 0. So we have a single byte value, and we have, when we have 255, it means all bits are equal to 1. But the question is, what is the value 255 plus 1? Do you have any idea? Yeah, int overflow. Somehow yes, but in C++, the overflow is not detected. So in mathematical sense, so in binary, yeah, okay. So look, if I add 1 here, wait a moment. Okay, so if I add 1 here, it gives me 0. So I move 1 here. So 1 plus 1 is 0. 0, 0, 0, 0, 0, 0, 0. So I have 8 zeros. And okay, at the 9th position, I should have 1. Yeah? Okay, it's obvious, but in memory, I have limited number of bits to represent this value. So this element is lost. So the result is 0. Okay, so look, it changes from the maximal value to the lowest value. Okay. Okay. So let's look at the standard integers. So the integers where the minus or negative and positive values exist. So look, in binary system, we don't have, also in IT, yeah, everything has to be represented using bits. So there are no extra characters like minus, for example. Yeah? So now I'd like to show you how the string of bits is interpreted if we use signed integers. So for example, integer int. Yeah? So look, 0 is still 0. So when we have 8 zeros, it means 0. When we add 1, okay, everything works like for unsigned integer up to 127. So for 127, we have 7 times 1, and the most significant bit is equal to 0. Okay, so now let's look on the negative part here. So look, this is 0 minus 1. Yeah? So when we have 0 minus 1, we can think opposite. So let's assume that we denote minus 1 as 8 times ones. And I'd like to add 1 here. So this is minus 1. So if you add 1 here, you get 8 zeros. So you get, in fact, 0. So it works. So it let us, this representation led us to perform mathematical operations in the standard way. Because if you add 1, you get 0. If you subtract 1 from 0, you get the representation like this. So the following values are, consequences of the assumption that 8 times or string consists of 8 bits equal to 1 indicates minus 1. So it works until we get minus 128. So we get the value where we have 7 times zeros, and the most significant bit is equal to 1. So look now, if you add 1 to 127, you get minus 128. So this is also the consequence of the notation we assumed. And what's more, here there are no overflow, because overflow exists here, and this is the ordinary, operation when you add 1 to minus 1, and here the single bit is changed. So, but the value of integer changed from the highest to the lowest one. Okay, so how we can cope with this problem? So how we can protect against the overflow? Do you have any ideas? Okay, yeah, of course. The simplest way is to allocate more memory. So here we have a single byte, but we can, for example, use integers, which consists of 4 bytes. So the maximum value will extend to 5 billions, I guess. Yeah, so we can expand the memory. In C++, the biggest or the largest type is long, so it takes 8 bytes. But do you think that it fully eliminates the risk of overflow? No. Yeah. Okay. So always there is a risk that the overflow may occur. But do you think that it is very serious problem or not really? Yeah. Yeah. Usually programmers, or maybe not all of them, but those who write some desktop applications or web pages say that, okay, I take a very large type, and okay, it never happened. Probably some of you know the Murphy laws, and Murphy law, so one of them says that when something may happen, definitely will happen. So so remember, several years ago in Poland, there was I think more memory to variables slows our program down. Yes and not, because when you have 64 bits processors, for processor, it doesn't matter whether it process 1 byte type or whether it process 4 bytes type. So or 8 bytes type. So because we have, you know, usually 64 bits processor, operation on integers or even long types works on the same speed. Yeah. But I'd like to tell you that several years ago in Poland, it was it consumes more RAM. Of course, yes. If you take, for example, characters, so ints to represent characters, you waste a lot of memory. Therefore, characters are a single byte integers. Or in UTF-8 encoding, which is the most commonly used encoding now, most characters are encoded using a single byte, because we can save a lot of memory. But if you have, you know, a critical values like counters, assuming that it will never overflow, it's not good approach. So several years ago, about 30 women were burned during radiotherapy. Yeah, this problem exists. Several years ago, it was, I don't know, in 2010 or 2015, there was a problem also with the clock. But now I'd like to give you another example. So the women were burned due to radiotherapy, and they have some oncological problems, or so cancer detected. And the standard treatment is that the dose of radiation is, you know, is get to destroy the cancer cells. But this operation has to be performed precisely. So if we have cross-section of, let's say, body, and the cancer cell is located, let's say, here, the radiation is given from different directions, but it is assumed that it focuses in this point. So in this point, the density of radiation is so high that the cells are destroyed, while outer, it is lower than the, you know, the threshold where the cells are destroyed. But the problem was that this women were burned, so the on the skin and in inner of part of body, some burns occurred. So that was the it means that the radiation dose was higher than safe. Okay. It was in a single hospital, but that was not so regular. So it occurred for some of them, not for all of them. So the there was, of course, they claimed hospital, and experts has to decide whether it was the fault of the machine or human error, or what was the source of this problem. what happened? So it happened that in the machine program, there was a counter. So the dose counter. So radiotherapist said that, for example, a particular a person should get, let's say, 100 doses of radiation. So the counter was increment from, let's say, starting value up to the by 100. And let's assume that everyone got this dose. But of course, the counter had a limited number of bits allocated. Okay, that's obvious. Every counter has. So the last one, so the subject here, should get 100 doses of radiation, but okay, this counter was not so the value was smaller than 100. So when it was incremented by 100, the counter was overflow. So in fact, they got not 100 doses of radiation, but this value, okay? So of course, the radiation was greater or significantly greater than the dose which should be applied. So this person were badly burned. Okay, so now we know what was the cause. So the problem is who fault? So is this machine fault, programmer's fault, or hospital fault? So maybe it's not, the problem is not related to computer science, it's more general, but what do you think? Programmers, so human error. Okay, which human? So operator or programmer? Yeah, okay. But you know, of course, for us, it's obvious that it was programmer. So I'd like to pay your attention to protect your code against such effects. It should be definitely protected. But in fact, the hospital was claimed because in manual, it was written that the machine should be restarted every 8 hours. So there was, so because it was not restarted, the counter overflowed. Of course, so programmer definitely should protect this code against the overflow. But but the manufacturer of this device protects against this kind of risk using lowercase information in manual. Okay, so let's go further now. Okay, the question is how we can protect against risk like this. So look, Of course, now I don't want to introduce the I don't want to introduce the conditional statements, but I'd like to show you how we can partially solve this problem. So look, the first way is if we have signed integers. The first way is that we can compare whether the resulted value is, for example, larger than the previous one. So it's enough if you know conditional statements. It's clear how to do it, but I can verify whether value is still bigger than the previous one. If you verify this condition, it will be clear if the overflow occurred or not. Okay, so this is I think the easiest way how to check. Yeah. Okay, so let's go further now. Okay, so now I'd like to tell you about floating point numbers. So I told you that everything is treated as, bits, so has to be expressed in bits. So how floating point numbers are represented if we have, for example, decimal point. I'd like to start from a quite simple example related to decimal system because it's easier to understand, and then we switch to binary. So look, if I have, let's say, 100 or 100.123, I can represent this value using two integers. So I can have 100,123 times 10 to power minus 3. So I have several elements here. Here I have something which is called a fraction. And here I have something which is called exponent. So using this notation, you can represent all or almost all floating point numbers using two integers. So the fraction is integer and exponent is integer too. Of course, there are some problems. So for fraction, we have to allocate specific, so some number of bits. So the result is that not every value can be represented in fraction because the number of bits is limited. So if it's limited, the value is limited too. So look, assuming decimal system, if we have 1, 2, 3, 4, 5, 6, let's say 6 digits, we can use to represent. And here we have, let's say 1, 2, 3 again. This part is truncated, so it can be represented here. So when we convert this value again, we get 100.123, and here there are no values. So so look, using this kind of representation, every value, or some values, can be represent only, as an approximation, yeah? So not strictly. Okay. So now I'd like to convert it into the binary. So look, if we want to do it on binary system, the base of the system is not 10 but 2. So in this case, what values are represented in binary system? So correctly represent all values which can be expressed as a sum of the values of power 2. So, for example, when I have 0.5, right, it can be represented as 1, 2 to power minus 1. But if we have 0.1, for instance, we can't represent it as, on this way, yeah, because it cannot be strictly approximated using using sum of power of 2, yeah. So but of course, for example, 0.25, okay, can be represented like this, yeah. So all elements has to be, so it works also when you sum them up, you can have 0.75 and so on. So all elements can be so you should know that there are some values which may be strictly represented and other are approximated. Of course, so look, for example, okay. So look, when I have a value of float a equals 0.1, and I'd like to see out it. Okay, it's 0.1, but when I increase the precision, see out, you can see that it's not really 0.1 because there is also some, additional elements. There are additional digits at the end. So, but if you take 0.5, for example, okay, it doesn't matter, it works, and it is always 0.5. What can we do? Of course, we can use double. So in case of double, it's 0.1, okay? But if you increase the number of digits, as precision, you can see that, okay, there still we have, you know, some residual elements. Precision 1000. Maybe. I haven't tried. Yeah, it's not 1000 probably. The precision, so the number of digits, it's limited, but you can see that the value, some values in floating point types, some values are not strictly represented because they has to be expressed in form of powers of 2. No, 0.1 doesn't exist not only in C, but it doesn't exist in computers which use floating points representation. So look, the single precision, double precision are standardized types, so they exist in all programming languages. They are supported by processor arithmetical, so floating point units. But you should be conscious that not every value can be correctly represented. Okay. Okay. So there are some serious consequences of that. I will show you them later, but remember, okay, if you have, you know, integers, okay, your value may overflow. If you have floating points, okay, the precision is limited. Of course, in case of floating point, not only precision is limited, but maximum and minimum values are limited too. So for example, in case of double precision, the maximum or maximal and minimal values are like this. What happened if you exceed the maximal value of float or int? Do you know? Is this, yeah, infinity? Yeah, so the value will have infinity. So the value will not overflow, but the infinity value will be set. So infinity value cannot be, you know, changed. So any operation with infinity gives infinity. So this is the result. In fact, in the standard, there are two infinity values. One of the value generates exception, other not, but okay, one is called a silent infinity, but okay, it's out of scope for this lecture now. Okay, so that's almost all about types. Now I'd like to start another lecture, which is very important for, you know, your programming skills. So it is about control flow in C and C++. So what do I mean control flow? Look, in our program, if you have a program like this, the program is executed from the first beginning from the first line up to the last line in your main function. If we talking about flow control, it means that we want or we may change this process. So we, for example, we can skip several lines. So the program may execute a single line and then go somewhere else. So this process is called flow control. But before we start, I'd like to tell you something about operators, which are commonly used in flow control schemes. So the first operator is plus plus. So plus plus increments value by 1. So I showed it. No, not yet. So it means that the value will be increased by 1 and assigned to this variable again. So look, but there are two kinds of operators. So it's post-incrementation operator and pre-incrementation operator. So in this case, I have counter equal to 1, cout counter plus plus. It means that first the counter will be printed, and after that it will be incremented by 1. So the incrementation is the last operation. Conversely, sorry, we have the code with pre-incrementation. So in this case, the first operation is incrementation, and then the counter is printed. So in this case, on the screen, 2 will be printed, but when you execute both of these lines, the counter value will be the same. So it will be equal to 2. Similarly, we have decrementation operators, so post and pre-decrementation, so they work the same, okay, opposite to incrementation 1. I showed you this notation, so if you want to increment by different value, you have to use okay, do you mean the floating point representation? Okay, so be patient. At the end of this lecture about flow control, I will show you how we can partially how we can cope with that. So there will be maybe not hint, but the standard approach. Yeah, remember that the floats and the doubles are not reflects decimal values. The decimal values is only printed on screen. They represent values in binary form. So it's not correctly. It's not correct that they limit amount of decimal places, but of course, I showed you very high precision. Yeah? So if you limit to precision up to 4 decimal places, everything is, hidden from this user. So she or he can't see it. Yeah, but double precision is usually enough for for representing even very complex very complex problems. So be patient. At the end of this lecture, I will come to this topic back. Okay. The second element I mentioned before is related about arrays. I showed you a string array, so how we can represent a null terminated string, so how we can store a text in our code. But the array can be used not only for characters, but for any type. So we can have array of ints or array of doubles. So in this case, it means that I have array with for 100 ints or for 30 doubles. So how we can get access to particular elements? So look. In array, every element in array can be accessed by using something which is called index operator. So here we have index of the elements. So index of the elements starts from 0 up to the value of elements -1, so 11. And if you want to write element into the array, it's enough to write the array variable name and index of the elements. So writing tab index 0 equal 5, it makes, or it writes 5 into this position. If you have the notation like this, you try to read value from the first element, so it's 5 plus 2, and writes it into the second element, so it's 7. So you can see that if you perform this operation several times, your array will be filled with values corresponding to arithmetic series of number. So every value is increased by 2. Okay. So the last, issue which introduce us to flow control are logical operators. So in case of logical operators, they are used to compare two values. So the result of logical operator or logical operation can be 0 or 1, true or false. Sorry, false or true. So in C, the false represents value 0. So and the true is represented by value 1. So what does it mean? It means that if we have, let's say, arithmetical operation, the results can be, from -infinity up to inf t. But in case of logical, so if you have A equal B, the result can be 0 or 1. Okay, so there are several operators. So this operator means is equal. Yeah, and usually, or maybe some of you make sometimes error that they try to change whether two variables are equal by using a single equal character. So it gives you totally different behavior in your program. So is equal, less or greater, less equal or greater, or equal, less or greater, and is not equal. So these elements are very commonly used to compare two values. Here we have logical operators, so we can combine several logical expressions, so logical expression 1, logical expression 2, by logical and or. So we can calculate whether we want to check if it's enough that any of this condition is true, or both or all of them should be true. So depending on the behavior we want to have, we have to use a particular logical or or and. And here we have a single argument operation, so it calls logical negation. So look, if I have operation like this and I use negation, it means it's not true that A is equal to B. Of course, in this example, I can easily represent it as A is not equal to B, but you can do it also on this way. Okay, so here you have several examples, and I suggest you to try to solve them by your own. We solve only a single, maybe two examples to show the way how to do it. So look. I'd like to show you to come to the integer precedence and look that the logical operations, they have smaller, so higher precedence, so smaller priority than other operations. So when you compare values, they have higher precedence than the logical, the and or operations. So let's go to this example again. Okay. So look, assuming that, so in this expression we have braces, but we can remove them and this expression will work the same. But you know, it's only for readability, for better readability here. So look, first we have to solve this elements. So what is the value of this expression? 6 smaller or equal 6. Okay, it's true. And 5 smaller than 3 is false, so it's 0. So now I have the AND. So AND assumes that both of those expressions has to be true. So the result is false because this expression is false. So here you have the same expression, but here we have or between. So it gives us the different result because it's enough that only a single expression is true. So the final value is also true. So I suggest you to solve the rest of these expressions by your own and try to understand how it works, why the value here is true or false. I think it's a good way to practice of logical operators. So tomorrow we start from the from talking about conditional statements. So from if and I tell you something about loops. But I think it's not a good time to start this this issue now. So tomorrow we have lecture tomorrow at 9:45. I guess we have only a single lecture, and in next week in next week we have 3 lectures. Okay. So thank you for your attention and goodbye.